First one, and following we are talking about the differential quantizer. So differential quantizer is look like we have so differential quantizer is look like we try to make a difference between the neighboring signal. So suppose be, for example, here we have your S of n will be summation SP of n. So SP of n is more like a prediction. So we can get a residue. This is mobile deviation. So deviation signal. So here may be residue. So here prediction is based on previous data. So you can see based on S hat n-1, S hat n-2, and multiplied by coefficient. So this one is based on decoder. So you can see it's not based on previous S of n. It's not based on previous signal. It's based on decoding signal. So you have to know S of n. If we are quantized, so we can get S of n over half. So before we quantize, we hope our S of n minus, so will be subtraction our prediction SP of n, and then we get R of n. So we can quantize, get supposed to be, we have to write down like index, should be index R hat of n. So go to channel will be index R hat of n. So more like this one. So I try to make it clear, quantize, we are get index S of n. So it's not a quantization value. After quantization value is index addressing. So this one, our prediction is based on this prediction is based on your decoding signal. So its decoding signal is based on your previous decoding signal. This one is based on S hat n-1 plus A1, S hat n-2 plus A2. So there will be summation, continuous summation. So here here equation just tell you we try to using from the signal, if like a speech signal. So if we try to predict this one, we are using their previous signal to do linear combination to predict this one. However, we are using previous one is not the original data. We are using decoding data, after decoding data. So because we try to using backward adaptive, it's not a forward adaptive. So backward adaptive is based on decoding signal to do the estimation. So the main idea we try, if you know the information theory, so if you know information theory, so we call the entropy. So if you have signal dynamic range is bigger, so entropy will be higher. After we take a differential, signal differential, the dynamic range becomes smaller, so the entropy will be lower. So entropy is lower, so we can use encoding. We can use less speed to encoding the data. It looks like your data diversity become smaller, so we can make a good use of our quantization level. So here you can see their differential quantizer here. they are using coming signal, so they try to subtraction your prediction, get a residual signal. So different signal, they are go to quantize, so they are get index. So index will be dequantized, and dequantized will be summation original signal to do the prediction. So suppose be this one flow chart should be changed here, should be changed like this one. We have S of n, so we try to do the summation. So this one is do the subtraction. So they are do subtraction. We using our SP of n. So we are do the subtraction. We get R of n. So they are quantized. So the quantized supposed to be go through channel is index. Index R half of n. So they supposed to be would be do the dequantized lookup table lookup. So we can get R half of n. So we are passed on. Okay, so I forgot here. So one more. So you have to do the summation here. You have to do the summation here. So this one will be summation back. We get S of n of half. Sn of half. So this one they will be do the prediction. So it look like they are buffer. This one is look like a buffer, and then do the prediction and next come in. So also, so you can see this one they have a feedback here. So our input signal subtracted by our prediction signal and get the residual signal and do the quantization. We go through channel, we are encoding bit is index our residual signal, quantized residual signal. So we are table lookup, recover back. So here we are Rn of half. So we have to plus this one back, plus this one back. So we have to be do the predictor according. So we are try to suppose be their subtraction. Later on will be add them together to recover back current signal, put in the buffer. So later on you are according as half of n minus 1, as half m minus 2, as half m minus p. So do the linear combination to generate your prediction. So they will be put in the here buffer and then do the linear combination and do the prediction. So you can see like this one. So this one they have a p component here. So this one is a buffer. So your new Sn will be put in the buffer later on for Sn plus 1. So here I make wrong. So it should be feedback here, do the subtraction. No, addition. Make an addition here. So in your textbook, sometimes they'll be confused the reader. We are go through channel is not a quantized residual value. Is go through channel is index, just index encoding bit. So you have to be dequantized and become the quantization residue. So quantization residue up here. So we have to add it back. So we have to add our subtraction value back, become dequantized signal. So in decoder, you can see we get the index. We get the index R hat of n. So you are dequantized. So we are get R n of half. And then they will be at Sn together. So as n of half, they have to be do the buffer. This one is buffer here, and then there will be linear combination. So they will be do the prediction. So they will be do the like summation prediction. So they will be generate the SP of n. So it should be here. This one is not a index, so they do the dequantize get of n. So in the textbook, it should be a little bit confused, so you have to make them more clear. So this one is called a differential quantizer. So you can see we do not have additional information sent to the decoder. So this one is a backward adaptive differential quantizer. So it's called a backward adaptive differential quantizer. Okay, this one is a little bit more complicated. So we have, so you can see here is we call the original one. So it's differential quantizer, and then this one is we try because we try to do the linear prediction. So you can see here we have a coefficient here. So sometimes decoder they want to know how to do the coefficient, because encoder decoder their coefficient should be known in advance. So here they show you we according input data, we have a buffer according the input data, maybe one speech frame could be 20 milliseconds would be 160 sample, or 30 millisecond for one buffer will be 240 sample. So we are trying to do the prediction, the parameter, try to get an A of k, and then because this one is a forward adaptive, so we have to quantize them, because A half of k goes through channel will be index. Tell decoder try to get the coefficient, multiply, they try to get the coefficient. So they try to get the coefficient here, encoder and decoder. So during the encoder, they based on original data, try to estimate the best one. However, because we have to send the coefficient to decoder, that then synchronize with the encoder. However, it's not an original coefficient. We are using a quantize, make the big smaller. So we are trying to using a quantize. So however, sent to the decoder is based on index a k of n. So decoder get this one will be recover the coefficient. According to the coefficient, they can do the prediction. So you can see this one is according original data, do the estimation, your prediction coefficient, and then go through do the coefficient, do the quantization. So send the index go to the decoder. This quantized coefficient for the prediction your current input data. Decoder will be get a coefficient and know how to do the prediction. So they will be get the index, and the quantize get the AK, A1 up to A1 half, A2 half, up to the AP half. So they know how to do the prediction and predict the current data, summation them back. So they have a retrospective data. So you have an additional overhead to tell decoder, to inform decoder how to do the linear prediction. So this one we call the forward adaptive. Okay, so here we are talking about later on we are talking about the vector quantization. So you can see here, so differential quantizer here. Why differential quantizer can work? Because our speech signal, their neighboring signal have a high correlation. So we can we can use a differential quantizer to do the work. So I will go back our textbook and show some part is missing before we go talking about the vector quantization. Okay. Speech processing. So Okay, so we are right now talking about quantization, chapter 3. So you can see what we're missing. Let me double check. Okay, so let me check here. So we have differential quantizer. Let me double check what we missing before. So we start from the beginning. Chapter 3. Let's go through the textbook and double check what we missing before. So in this chapter, we are talking about, in the beginning, they are talking about a sample. It's very straightforward because we have our speech signal is goes through is a human being to pronounce the voice. Sorry. The frequency is lower. Used to be lower than 4K. So most of the speech processing we are work on 8 kilohertz sampling series. So you try to make sure satisfy Nyquist frequency series. So make sure we do not have anything. So this one is supposed to be you should be well prepared, have this kind of knowledge in your undergraduate courses. So first issue is scalar quantization. So you have to know delta is a quantization step. So and then this one, y is output, as the input is your input data, and then do the quantization. So y1 is quantization level. So s is continuous mode, the data is continuous. So however, S4 to S5, they will be using Wi-Fi to represent it. Wi-Fi is one value, however, Wi-Fi encoding bit is 100. So later on, we're talking about the quantization error. So this one already present in our presentation file. So today we just briefly review because we are talk about detail in last lecture before. So this one we are go through it. So one is a uniform quantizer, so the step size will be equal. So you can see they can satisfy this one, your dynamic range equal to your step size multiplied by your how many quantization level you are using. So you can see you can get it like this one, and then later on they can get a 6 dB. So this one you should be well catch in mind. Try to remember. For probability density function. So according such a condition, so you can improve the performance. Just increase your quantization bit. So maybe from 4 bit to 5 bit to 6 bit, increase 1 bit will be double. Increase 1 encoding bit will be double your quantization level. So you'll be increase 6 dB signal to noise ratio. So another one. So we sometimes we try to make sure your good quantizer. So we already talked to you. If we know their probability density function, so input signal probability density function, we can design a good optimal quantizer based on partition your probability density function in many regions, and then that integration area will be equal. According each region, we take centroid. That centroid point is your optimal quantization level. So this example just show you our data frequently come out could be as S3 and S5. So you can see quantization level S5 and S4 is more closely. And then later on S7, S8 and S7, the step size will be bigger. So indicate that that signal in this region is not come out frequently. So this one is a non-uniform quantizer. Another one, logarithmic quantizer like Arrow and Mueller. So this one we already talk about that. Another one is adaptive quantizer. So one we call this one is consider your variance here. Suppose be this one we call the standard deviation. Variance is a square. So depending on how to define, they assume the signal mean is 0. So you can define this one is your standard deviation. Variance could be square. I'm not sure. Should be double check for that. Okay, that process. So this one you can see we already talking about. So you have to remember what's the forward adaptive and what's the backward adaptive. So you should be know for that. One word memory. So we are not consider many word decoding word to do the prediction. We are consider previous data to do the prediction. We call the one word adaptive. Okay, so differential quantizer is based on previous prediction signal. So we are based on prediction. The prediction can be based on your decoding signal multiplied by coefficient. So here we are consider previous p number of p dequantized sample. So you can see. So this one you are do the pre-processing, make your signal entropy become lower. So make your quantization level quantization can make good use your quantization level, make your loss quantization loss degradation become lower. So this one is a backward adaptive is based on decoding signal. We do the prediction. However, here we prediction have some coefficient. So they also show you the coefficient that based on original signal. However, coefficient sometimes you do the prediction you can base on decoding signal, depend on you. But however, based on input signal, you are do the prediction can do the good prediction value. Okay, so in my presentation file, I just miss one signal here. So I try to show you here. So the performance differential quantizer, so you can approximate defined by his prediction gain. So amount of signal reduction before quantization. So the performance residual error quantizer assumes that the same type of quantizer is used for both differential or non-differential quantizer. So you can see here they try to do some formulation derivation. So they try to simplify. So we are not using P. Consider a previous P number, P signal. We just consider previous signal to do the prediction. And also we are assume the signal, the quantized signal, the quantized signal could be close to original signal. We try to know your residual signal. So we assume, make it easy. So we are original signal, we have a, so you have to be know, right now, suppose we consider a previous P component. Right now P equal to 1, P equal to 1, we only consider previous one to do the prediction. And also we are try to make our mathematical equation simple. So we assume S of SLN minus 1 reconstructed signal close to original signal. So our R of n is current signal subtraction minus your prediction coefficient according your previous signal. Supposed to be like this one, decoding signal. So we are approximate like this one. Try to make it simple. Okay, so right now we try to know what's the A would be better. So this one A they call the weighting. They call the weighting coefficient. Weighting coefficient. Okay, so we try to know what kind of A, what's the value of A. So we define we try to make a good prediction. We try to R of n minima. So we try to know if possible make R of n is minima. If our signal is DC term, so if we are doing like this one, A, so if we are using, if our signal is DC term, like a DC value, only DC value, so during the subtraction, this one is your S of n, and during the subtraction, R of n will become the 0. All the signal become the 0. So if you are DC term, so we hope if you are select the good prediction coefficient, weighting coefficient, do the good prediction. We hope to your R of n try to close, dynamic range become smaller, or try to hope your R of n close to 0. Try to make sure they are close to 0. So we try to calculate here, we calculate your square error because we try to do the prediction and then get a residual signal. We call this one residual signal. So we try to make sure your residual signal become the smaller. So we hope R square n equal S of n, because they have a positive and negative. So we try to make them square, and then if we are try to make sure R square n, try to open it, try to take the open it, you can see the S square n minus maybe take this one S square n minus 1 minus 2a S of n minus 1. So this one is like your neighbor signal correlation. So this one is look like a neighbor signal correlation. So this just one simple this one just one sample, and then we are consider one speech frame. If we consider one speech frame including n sample, try to according n sample find the best one, best value of A. We try to find the best value of n A. So we can summation here. So n equal to 1 n. So we are total distortion will be summation then together. You can do like this one. So it's minus 2a. So minus 2a. So you can see here n n equal 1 Sn. This one is look like we try to calculate one speech frame, their auto correlation. It's not a neighboring signal correlation. So later on, they are trying to simplify the equation. So this one is our residual signal variance. Is variance. So it's really like we calculate the energy, residual signal energy. So this one is look like our signal energy. And this one, we assume A is independent, your index n. So the A will become the put in the outside here. So our summation, as summation, your signal energy, this one and this one, just one signal deviation. So they are missing one and get new one. So this one and this one, so their energy signal will be similar. So we are using same like a one speech frame. If n is large enough, so these two will be close. And then you are subtraction a, so you can get n equal to 1. So we have s of n minus 1. Okay, so here they try. Sorry, I drink the water. So you can see here, they already define. They define another symbol. So like here, they call this one is normalized. They define another symbol here. They code, because this one is your signal correlation divided by your energy. So this one is a normalized autocorrelation, normalization, normalized autocorrelation coefficient. So previous of what we say here, so you can see our rho r square, rho s square. So we have a rho s square. So you can see 2a. So this one just autocorrelation. So we are try to use a normalized autocorrelation. So you'll be normalized autocorrelation will be rho s square times, how to call this one? We are called, I assume we call the rho and this one. Right now I'm using the r. Maybe we call the r first. I forgot the name. Okay, so you can see this one is our energy. So you can see it will be rho s square. So this one multiplied by this one become original correlation signal. So this one multiplied by here, so you can get it like this one. So they define one called the prediction gain. Prediction gain here. So you call the GP here. So the prediction gain, we try to make sure original signal energy over your, because your residual signal energy, we want to this one maximize. So like original, we have a DC term. So you take a differential, residual signal become 0. So the prediction gain, this one divided by 0 become infinite. So your signal and entropy will become lower. So that one will be make your encoding easy. So we try to define your original signal power divided by your residual signal power, because you already do the prediction. So you can reorder. You can reorder here. So you can see rho s, we are trying rho s here. So you can rho r square. So is rho s square 1 plus a square minus 2ar here. So we try to rho s square by rho r square. So this one move here. So this one move here. So you'll be 1a square minus ar. So here. So because we try to make this one maximum one. So denominator, this one denominator. So we try to make this one bigger one. It looks like we try to make this one smaller. So if we reorder it, so you can see we try to make this value smaller. So you can see a squared minus a rho plus 1. So this one is related to signal. So related current signal. So they could be the fixed value depend on right now our speech frame. So this one depend on current input. This one it depend on your speech frame, current input speech frame. So we try to make this one minimum one. So in your high school, we already teach this one because this one is a positive value. So you will look like a like this kind of curve. So like a you have defined by your maybe this your y. So y, so you'll be more like we have a minimum value. So we can do we take because the variable parameter is a. So we try to partial then take a partial then we try to 2a minus 2 rho 2r equal to 0. So we take that derivation. So this one we take a partial derivation. So you can see here if we try to find their derivation become the 0. So this one will be your minimum one. So you can see your a will be equal to your r. So it look like what they want to say. If you are trying to do one previous data to do the prediction, the maximum your gain, your GP gain, here you call the GP gain would be here. Your GP gain, we are GP gain here. Here is GP gain. So here you'll be become r squared to r. So you'll be more like this one. So if this one tell you what do you see if you are just one prediction gain. So your prediction gain, best prediction gain is here. So normalize autocorrelation. If your neighboring signal are the same, so this one could be close to 1 or close to 0.9, close to 0.8 because your neighboring signal very close, very similar. So you can see this one is the energy. So this one neighboring signal. I assume your neighboring signal, if your signal is DC term, all the data are same. So Sn is equal Sn minus 1. So your numerator and denominator, they dividing all the same. So they will be equal to 1. So your prediction gain will be infinite. So you can see here their conclusion here. So autocorrelation between adjacent sample is high. So differential quantizer will be performed significantly better than non-differential quantizer. So if your neighboring signal highly correlated, what's the input signal highly correlating? Based on your normalized autocorrelation. If they are signal close to 1, so neighboring signal highly correlated. So they are highly correlation. So if the correlation between adjacent sample is high, so your differential quantizer will be perform significantly better than no differential. No differential quantizer is not a signal. You are quantize signal directly. It's not do the prediction using your previous data, using your previous decoding data do the prediction. If you are using your previous decoding data do the prediction, because your neighboring signal have a highly correlation, so you can get a better prediction gain. So the signal can be quantized is a non-varied DC term. If you are DC term, so your rho is R equal to 1, so your prediction process prediction gain will be infinite. So no residual error will be left. So no residual information will be need to be transmitted. So typical R rho for speech between, so speech signal around 0.8 and 0.9, so it can be make because they are highly some correlated, so you can result 4 to 7 dB signal reduction before quantization. So you can see our before quantization, our signal the deviation will be make then reduction, so can be increase your quantization performance. So the main idea here, because our speech signal is highly correlated, neighboring signal highly correlated. Right now they code 0.8 or 0.9 depend on your signal variation. So if you do the differential, this one original signal. So if we are R of n could be make the signal become more dynamic range become smaller, and then also make the performance better. So right now this derivation tell you if just one order do the prediction, prediction depth, predictor depth is 1. So what's the best A according to this derivation, they tell you the best A is this one. This one is a normalized autocorrelation coefficient, can do the good job. Okay, so main idea here, what we want to do here, because you try to do the quantization. So first issue here, what we call the signal, original signal. We try to do one issue, try to reduce the signal, the entropy. Try to reduce the signal entropy. Maybe the other word, try to reduce signal the variation. So the signal, the dynamic range, you try to reduce signal dynamic range, signal the variation, make it more consistent and simple. And later on we do the quantization. So because the quantization, what's the meaning? Quantization, we are using limit. We are using the limited number of quantization level. We are using limited quantization level to represent the diverse data. So we are do some pre-processing, make the diverse data maybe become a little bit simple. It's not so diverse. So it's not so diverse, make your quantization prediction gain better. So the main idea is to try to make your signal entropy become the not so variation, not entropy lower. So you can see previous what we talking previous like a adaptive quantizer, they try to divide it by their dynamic range standard deviation. make the variation become smaller, so we can design unity gain quantizer and something like that. So it looks like we are trying to make your signal become uniform, so make the data easy to do the quantization. Okay, here before I go to the vector quantization, so I'll be using Mandarin, a little bit repeat what I said before. OK， 那前面我们构述课本大部分都讲过了，那比较投影片上比较没讲到的是刚才我所课本这一段啊，课本这一段主要是说我的语音讯号它的因为语音信号它你自己发声不可能这个 sample 跟下一个 sample 有很大的变化，因为人的喉门的开关已经 sampling rate 已经把你抓到了只有 4K， 所以说在相邻的 data 你的嘴巴嘴型不可能变那么快，那实际上相邻的 data 在取样后都有相对的关系，那课本说大概有 0.8 0.9 看你的讯号，那有些人讲话可能变异比较快一点点，但相似度就会差一点点。那如果课本做了一个简单的推论，如果我根据前面的讯号去做预估，那为了简化推导，它先用原始，正常的推估不可能用原始讯号做推估，一定要用 decoder 端来做预估你现在讯号。我得到的剩余讯号，接下来呢，我会去算，我的目标是要让我的剩余讯号越小越好，它的变异性越小越好，也就是 entropy D 的值的变异性越小越好。然后这个值，所以说它就把它做平方，最后推演了之后呢，你会发觉你的最佳的预估系数实际上就是我的讯号的correlation 除上它的能量，形成了 normalized 的 auto correlation，normalized auto correlation， 这个就是你的 A， 那实际上就是你的最佳 prediction。那某种程度，如果你是一个 DC term， 那你就会发觉，如果会得到它是一个无穷大的 prediction gain。在这个推导当中，你会发觉实际上我们想要求的 A， 那 ρ 呢，当然是这个是根据你的讯号的 correlation 的能量。当你的音框进来 n 个音框进来，讯号固定了，你的这个值就是固定。那唯一的针对这个音框，我到底要决定什么样的 A？ 那这时候呢，这时候就是它是一个2次式因为我要 prediction gain 最大，那它的是刚好在分母，代表说什么？这个越大，代表分母要越小。那这个是2次式，那它的2次式 A 是变数，我要去找最佳值，它的2次式上面是正的，所以说它是一个抛物线，有极小值。那我对 A 做微分，得到 A 等于它的 ρ。那实际上某种程度实际上就是 A 等于这个值 normalized auto correlation 可以得到较佳的 gain。好，那这个就是为什么 differential quantizer 在很多早期语音处理的时候 ADPCN 都会用。So differential quantizer in the beginning we are talking about speech coder. They are spend a lot of time. They talking about ADPCN. So why they using the ADPCN? PCN, adaptive Pascal modulation, adaptive differential Pascal modulation, because that one is according we are trying to take a differential between current input and previous decoding signal and make the variation become smaller. So make the quantization efficiency better, quantization gain better. So that is the main purpose. Okay. So another issue we are talking about the vector quantization. So maybe we cannot finish the vector quantization. I'll be highlight what's the vector quantization. So another way we're talking about the vector quantization compared to the scalar quantization. So you can see the vector quantization. So vector quantization is scalar quantization is one component maybe S1, S2. So So for each component we are do the quantize. So we call this one like a scalar. So it's a scalar quantization. So vector quantization will be considered minima is two components together or more data become a vector do the quantization. So they are considered like this one to do the quantization. We call this one is a vector quantization. Why used to be vector quantization performance vector quantization performance better than scalar quantization, because the scalar quantization we are quantize the data discretely. Why? Because we are partition them, so they have some correlation. We are not considered. We are considered independent quantize. So in the previous what we talking, we try to not quantize the original signal. We try to quantize the residual signal, more like do the using neighboring signal, do the subtraction, prediction, and make the signal dynamic range become smaller. So a little bit consider your neighboring correlation. However, scalar quantization performance is not good like a vector quantization, because they partition the signal discretely. There will be loose correlation between neighboring signal. So vector quantization will be considered neighboring signal together to do the quantize. However, there will be loose between the vector. Between the vectors, the correlation will be loose. The correlation between the vector. And then this one, scalar quantization will be lose the correlation between the sample. So this one, scalar quantization, they lose more because they are sample based. Vector quantization, they just lose a vector between the vector. Like an image processing, we call this one like a blocking effect. If you know image processing, this one is related, more like related blocking effect. For image processing, like a one image, we are like a JPEG. So they are using 8 by 8 to do the image processing. So the neighboring signal 8 by 8, they did not consider this block 8 by 8 and neighboring 8 by 8 because they are trying to encoding based on 64 components to build out some model, try to find some model coefficient. So they did not consider neighboring block, the boundary information. So this one we call the blocking effect. So more like a vector quantization, you did not consider neighboring vector correlation. This signal, supposed to be they are neighboring, they have some correlation. So what's the quantization? Quantization is from your signal, try to find some redundancy, remove the redundancy, make your signal easy quantize, and try to from your signal, because we try to find representative. So also, if we try to give them the quantizer more information, they can do the good job. If we are give them the data independently, sometimes the model cannot model signal better. So quantize is the other word. So you can see they try to know, maybe you have some redundancy. We have to make sure that redundancy we can give up that one. So right now, why we talking about scalar quantizer performance is loose than vector quantizer can do the good job better than scalar quantizer because they are considered more data correlation, and then however they have a vector correlate. They will be also have a blocking effect. But a scalar, they have a sample independently, so they will be lose the data between the correlation between the sample. Okay. So vector quantization, so basic idea. So is a set of discrete time amplitude value. So a group of them, a vector of them, are quantized jointly together as a single vector. So the process is known as vector quantization. So sometimes block quantization or pattern matching quantization. So your input data so become the vector. So they will be do the vector matching. So they have a code book here. So you can see here they do the right word. This one is index I. So you have to know our input data S of n. So they have a buffer. So become vector input here, big capital. So you have a many component, and then the vector matching. You have a code book here. We call this one is code book. So inside there we have a covector. So each one we have a covector. The next one we call the code book. So they do the matching. So this vector in your code book, this vector will be calculate distortion with input vector, and then you have a many vector will be matched with your input data and try to find which vector code book inside the code book, which vector will be minimal loss. So you have a minimal distortion. Which covector have a minimal distortion? The code, for example, covector you have a 1024. So each covector, the index will be 10 bit. So index will be 10 bit. So you can treat this one like a memory. I using the memory address. So it's 10 bit. Try to from your memory to get one vector come out. This one best match your input vector. So what you send out is more like an index. We can say your code book, maybe we can say code book the memory address, like this one. Okay. So this one just show you one simple idea here. So vector quantization, minima the component is 2. So they give you some example here, like a 2-dimension. So you can see the 2-dimension here. So you have a 2-dimension vector. So you can see we try to clustering your 2-dimension space. So you can see this space, for each partition space clustering, we take the centroid here, and then this dot point is our covector. So you can see here our input data, our vector here, our big vector here, our vector input vector. So our input vector is S1, S2. So you can see like a S1, S2, and then you can see they partition many clustering region. So in this region, this point S1 coordinate, S2 coordinate value is their covector. Covector here. So if your data belong, for example, you have a data distribution like this one. You have a many data distribution. full quadron. So if you have a full quadron, so if data here, so our quantization, this one is our quantization quantization covector. Covector. So this covector is in this region, sometimes like a centroid point. So this region, they have a S1, S2 coordinate value. So coordinate value coordinate value is their represented covector. Sorry. So here they show you distortion. Covector calculate the distortion. So the simple one, you can see this calculate distortion. So we try to say here what we're talking about, they try to find the winner, try to calculate the minimum distortion. So because you have a many covector, so you have an input vector. So input vector will be do the cobalt search. We call the cobalt search, and then they'll be do the vector matching. So this one will be first covector. They calculate distortion. This coming vector will be compare with covector 2, and then try to find out how calculate distortion with whole vector covector. Try to find which vector is a winner. That winner is have minimal distortion. So this information show you we have a two covector. Y is inside your covector. S is your input data, input vector. So they try to from each, for example, your vector dimension is n. N is including here we have a covector n component. So n component here. So you can see each component subtracted by corresponding component in your covector. Try to calculate the distortion. They have a positive and negative. So we are trying to take if we are some it's not original data. So they have a preprocess to generate some feature. The feature they have some important part. Like if we using the FFT, like you are doing FFT become the frequency domain, maybe that vector low frequency component have a more important part. During we are trying to calculate distortion, each component we have to multiply the weighting function. So during our calculations, calculate distortion, this component subtract by this component mean square error, try to take a square and then multiply the weighting function, because maybe this component related low frequency, they are more important. Could be the ratio will be higher, 0.2, the other could be 0.15, 0.1, maybe their weighting value will be lower. Make our try to highlight more important component. During your calculate distortion, can highlight that component important part. This one is sometimes from your perceptual point of view, from your quality point of view, so you can do some weighted mean square error. So maybe so we are trying to rewrite here. Weighted here is more like this one. So you have a WK SK minus YK. So yeah, weighted function here. So they are using here just using the other formula. That one similar like this equation. So another one is a binary search codebook. Binary search codebook is talking about if you are trying to do the full search your codebook. So if you have a 1024 covector, 1024 covector. You have to do the vector matching 1024 times. So each one you have to calculate distortion. So you will take a lot of time. If possible, we are transfer your cobook become the tree cobook, like a binary tree cobook. You can be triple, quarter tree cobook because the final covector is 1024. However, the level could be 1, 2, 0, 2, 1, 2, 2, up to 210. So first one, maybe we do not need this one. We try to compare this one. Try to find two vector. Which one is minimal loss? If winner here, they will go to this path. Try to find a winner. So total cobook search, covector mapping. So your covector matching only 10 times. So you are reduction from 2024 times covector matching reduced to 10 times, because you are supposed to be your full search. Each by each, do the full search, try to calculate the which winner covector with minimal distortion. If we are from our codebook become binary codebook, so become binary codebook, we can only compare the winner 10 times. Try to compare 10 times. So total each level just two covector comparison, covector matching. Total only 20 covector matching, matching operation. So this one full search will have a 1024 covector matching. So if you are build on your covector become the tree, that one reduces your covector search to find the winner. However, full search can get the best performance. Tree search sometimes go to wrong direction. You cannot find the best winner. Maybe best winner here. However, in the beginning, your tree go to different wrong way, so the winner becomes the other one. So sometimes you reduce your covector searching time, but the performance could be is not the best one, is the second one. Second best or third best. Okay, so I using the Mandarin, repeat what I said, vector quantization. 那向就是说向量量化，实际上最少会考虑两个元素以上，两个元素形成一个 vector。那传统的 Scalar quantization 因为把原来的讯号呢当成 discrete 来量化，它讯号之间的关系是没有考虑进去。所以说，在你建量化 level 的时候，只看进每一个讯号的特性而已。那 vector quantization 当你做量化的时候，是考虑这一组讯号之间的关系去建构它的量化器。那唯一的是这一组跟下一组之间的 vector 的关系就没有考虑，也就是传统说的 vector blocking effect。那也就是说，如果我要去做量化的东西，如果我给你整张影像让你去建 model， 你可以有效的去建出好的 model。我如果只给你部分资料，你去建model， 当然你的效果不会最好。这个道理就在这里。所以量化呢，实际上就是在原来的讯号找规则，找某种程度的规则。你越有规则， 我可以找到某一个 rule 去代表你的讯号，那这时候我就可以压得很好。那你的讯号越乱，你的 entropy 越高，你的讯号越不乱 entropy 低，我同样的量化器效果就好了。所以说为什么以前常说 entropy coding 实际上就是无失真量化的一个代有名词。那量化 vector quantization 向量的量化不外乎就是你会设计一个 codebook 将来呢进来的 vector 呢都会根据你的 codebook 做比对。那如果你有1024个 covector 形成的 codebook， 那你会从1024里面去每一个 covector 都要做比对，这个叫做 full search。那比对完某一个 covector 1024个 rows 当中 distortion 最小的就是赢家，那个赢的 covector 就变成你压缩的 index， 那实际上就是 address。 你绝对不是送 covector 这个代表到 decoder， 因为 decoder 端跟 encoder 端都会有这个 codebook 相同的 codebook。 那当然你说将来可以做 adaptive codebook， 当然就有 backward 跟 forward adaptive 的机制，但是之后再讲。那另外一个呢，如果你像量化的时候，实际上像刚才举的二维空间某个区间的 data， 我实际上就是找量化的代表点，也就是说我用较少的代表点代表复杂的空间，一定有失真，这就是量化的精神。只是说我的代表点怎么选，让你的失真的值越小越好。然后刚才是讲 full search， 如果 full search 像这个1024个 covector 形成的 codebook， 我要做1024次的 covector 的配对比较算 distortion。 如果我把这个呢建构成 binary tree， 你也可以是它的上有3个或上有4个，那如果是 binary tree 呢，每一层呢，那最后一层当然是1024个，那你会发觉我们每一层只要搜寻2个，那 total 搜寻20次就可以找到 winner。 但是呢，如果你第一次走的路线不一样，说不定你如果做 full search best match 是这个，那这可能就是你的第2好第3好，不见得是最好。那但是你减少了应该是20次，你的 covector match 是20次，原来是1024次的 covector match，这次变24，搜寻时间变少，但 performance 可能找到是少 optimal。 OK， once we talking about become the tree search, the covector matching is not a 10 times, it's 20 times. Each level they have to compare, go to which path is good. So you have to find out. So each level they have 2 covector match. So total covector match is 20 times covector match. Original full search is 1024 times. So this one just briefly talking about the vector quantization. So entropy is try to indicate how variation of your signal. So if we give more signal to build out your quantizer, you can build out a good quantizer. If you give the small number signal, you did not give them more relationship, sometimes your build out model is not good. Like image processing, if you give them the whole image, let them build out a model to model the original signal, they can do good job. Do good model to model original signal, original image. If you give them the image subroute to do the model, so they could be maybe the performance may be not good because their data information is limited. So same idea. Okay, I stop here. Next week I will be talking about the k-mean. So that one will be typical how to do, because our transparency did not show you k-mean. So I will be teaching you next week. I will teach you how to generate generate the better maybe it's not a optimal codebook, better codebook. I will teach you how to generate a better codebook. This one is most of them using the k-mean method next week. So I stop here. and talk to you next week. Okay. If you have any comment, send me an email regarding we are using online lecture using the online lecture. So because if you are online lecture, so you did not catch what I say, so because we already recording, so on the YouTube, so you can double check, pass through it, and make sure you catch the point after you pass through the textbook or something in the future. Okay, I'll talk to you next week. Okay, bye bye.